In the last century, we have learned a lot about the universe. First, Einstein came up with his general theory of relativity, and then Hubble discovered the expansion of the universe. Many other discoveries were made, and new theories, which explained the observed phenomena, were made. The Big Bang is the most accepted model, and the data really supports it. We have evidence that the universe has a beginning, and it began with a Big Bang. But is it the ultimate beginning? There are scientists who do not agree with this model. Roger Penrose won the Nobel Prize in Physics in 2020. In 2010, he came up with his own model of the universe, which says that the universe might not have a beginning as we all think.
In other words, there is a Big Bang, but the Big Bang was not the beginning.
Penrose provided us with a new framework, in which there was another universe before the Big Bang, and there will be another universe after our universe ends. This model of the universe is called conformal cyclic cosmology. Join us as we dig deep into how Roger Penrose's theory defies traditional views and offers innovative directions for cosmological research. But first, let's start with the general framework. Most of us have heard of the Big Bang, the notion that the universe began from a very hot, very dense, and very uniform state, and then expanded, cooled, and gravitated, eventually giving rise to protons and neutrons, atomic nuclei, neutral atoms, stars, galaxies, and a vast cosmic web of structure where within individual galaxies, things like heavy elements, rocky planets, and even life can eventually form. However, the Big Bang couldn't have been the very beginning of the story, as a number of physical puzzles simply go unexplained if we insist on it. Why does the leftover glow from the Big Bang, the cosmic microwave background, have the same properties in all directions, especially if these distant, disconnected regions have never had time to exchange information with one another? Why does our universe, where the combination of energy density and the expansion rate determines its curvature, appear perfectly spatially flat, rather than either positively or negatively curved? And why are there no leftover high-energy relics from this supposedly arbitrarily hot phase that the universe would have achieved early on if the hot Big Bang truly represented the beginning of everything? One possibility, famously noted by Alan Guth in the late 1970s, early 1980s, is that the Big Bang wasn't the beginning, but was preceded by a state of exponentially expanding empty space, which precedes and sets up the hot Big Bang. Further details were worked out by many, including Guth himself, André Linde, Paul Steinhardt, and Andreas Albrecht, as well as several others, concluding the following. In an inflationary universe, space was filled with a type of energy inherent to itself, perhaps some type of field energy similar to today's dark energy, causing it to expand not just rapidly, but relentlessly and without bound. When inflation comes to an end, all, or at least, most of that energy gets converted into particles and antiparticles, initiating the phase of the universe we identify with the hot Big Bang. But now, because of inflation, different regions all have the same temperature and density because they all emerged from the same inflationary state. The universe that emerges appears spatially flat because the inflationary process stretched it so that it would be indistinguishable from a perfectly flat appearance, just as your own backyard appears flat on the surface of the Earth. And there are no leftover high-energy relics because any pre-existing ones were inflated away, and the maximum temperature that the universe achieves when the hot Big Bang begins is now insufficient to create them again. In other words, inflation not only reproduces the Big Bang's successes, but it solves all three of the major physical puzzles that plagued the Big Bang beforehand. This lovely story was off to a compelling start, explaining the problems of uniform temperature, observed flatness, and the lack of high-energy relics that the standard hot Big Bang scenario struggled with. However, mathematical theorems established by Hawking and Roger Penrose reveal that inflation fails to escape the initial singularities present in the Big Bang. In fact, inflation itself succumbs to its very own Big Bang singularity. So, while our theory of the Big Bang is supported by a wealth of observational data, there are plenty of mysteries to satisfy the curiosity of generations of cosmologists. After all, if everything, including time itself, came into being at the Big Bang, how can we discuss what transpired before time existed? Fortunately, bold cosmologists have peered beyond the Big Bang singularity, seeking alternative explanations that transcend the conundrums of infinities and the origin of time. One intriguing notion suggests that a cosmic epoch preceding the Big Bang gave rise to a new physics paradigm, effectively replacing the singularity. The theoretical physicist Roger Penrose advocates for this idea by a theory called conformal cyclic cosmology. In his theory, as the universe tends towards its final state of cold, disordered emptiness, the notion of time starts to lose meaning. Even more, the large end state of the universe starts to look like a very small starting point. In a way that may be somewhat hard to grasp, the end of the universe starts to look a lot like the Big Bang. It's a counterintuitive notion and, of course, like many good theories of nature, it requires a mathematical description to fully understand. But the conclusion of the conformal cyclic cosmology is clear. The final state of a universe could be the beginning of another. If this theory is correct, our universe is one of an infinite lineage of universes and will ultimately become the progenitor to the next in the chain. And the Big Bang is both the start of our universe and the death of an older universe that came before. But how is it possible? To understand Penrose's theory, let's take a look at Higgs field. Higgs field is a field like other fields that exist in the universe. When particles like electrons and protons move in the universe, they also interact with this field, and this interaction gives them their masses. The more a particle interacts with this field, the more massive it gets. In the field theory, every field has a corresponding particle. For example, photons are related to the electromagnetic field, an electron is a fluctuation in the electron field, and so on. Similarly, the corresponding particle for Higgs field is the Higgs boson. The existence of the Higgs field can be confirmed if we can find the Higgs boson. In 2012, scientists were colliding particles using the Large Hadron Collider at CERN. They discovered this particle and confirmed the existence of Higgs field. Scientists now know that after the Big Bang, the universe was very hot and dense, and at that time, the value for the Higgs field was 0. But as it expanded and cooled down, the value for the Higgs field also grew, and it did it spontaneously. When Higgs field was activated, it, as told, gave masses to the particles, except for those which didn't interact with it, like photons. But according to Roger Penrose, before the Higgs field was activated, everything was moving at the speed of light. And at the speed of light, there is no distinction between distance and time. As at the speed of light, according to Einstein's special theory of relativity, the universe is like a point. You can't know what the time is or how far you have traveled. When we look at the future of the universe, Roger says, we find the same state. As the universe continues expanding, everything will be ripped apart, and ultimately the stars will die and the black holes will evaporate. There will be only photons in the universe. As the photons travel at the speed of light, there will be no way to know the time or the distances. So the universe will be like a point with no time. What else can have the same properties which I just mentioned? Remember the point where it all started? Which banged, and we got the universe. This is what Roger thinks of the far future of the universe. When Roger was asked this question, he smiled and said, well, infinity is a perfectly good place. So, does that mean our universe will exist for an infinite time? First, it doesn't make any sense, because if we think of the previous universe, and if that universe has to wait for an infinite time to end, then how come ours? To answer this question, let me first add a few things so you can get the idea. How do we measure time? We have the technology and advanced methods to accurately measure time, but in the essence, mass is the key. Without mass, we can't measure time. Here are two equations from physics that play a key role. One is Einstein's famous equation, which says mass and energy are the same things, and the other one is Planck's equation, which states that energy and frequency are interrelated. So, when we put these two equations together, we see that mass is related to frequency. So, in a sense, each particle in the universe is a perfect clock. In other words, if you don't have mass, you can't measure the time. One more thing, you can't find the distances either without mass. The best measurement of a meter so far is through the speed of light. 1 meter is the distance light travels in 1/299,792,458 seconds. Now, you know how important mass is in measuring distances and time. Now, again, imagine a universe with no mass and only photons. How would you calculate time or distances? You can't tell the difference between small and big. This is what Roger refers to as his infinity, and the term he uses for one cycle of the universe is aeon. But how did this transition happen from a universe with no mass to a universe like ours? Roger answers this question by saying that you might not be able to make sense of that, but mathematics tells you that it can and it does. So, this was the conformal cyclic cosmology. Many scientists disagree with Roger and have criticized his theory, but he is determined and thinks that his theory makes perfect sense. Recently, different ideas have been put forward by different scientists that explain the methods with which we can test if this theory is true or not. We will know in the near future if Roger is right or wrong about his picture of the universe, or maybe the universe will get further complicated. Elsewhere, some physicists also suggest that the universe we experience is just one of many. The concept of a multiverse, universes like our own but also slightly different, comes to us from two places in theoretical physics. One is from quantum mechanics and our attempts to understand the many branching possibilities found in subatomic experiments. The other is a little more concrete, coming from our theories of the extremely early universe. But to get to the multiverse, we have to start with just the universe. By definition, the universe is all the things. It is the sum total of complete physical existence. If it's a thing, it's in the universe. But even with that definition, we can start to crack the door to other universes. One way to do that is to recognize that the universe is only so old, and light can only travel at a finite speed. So there's a limit to what we can observe in the universe. That limit is about 45 billion light-years away. However, that explanation gives you a very weak vision of the multiverse. Actually, there's more to the universe than what we can observe, so there's more stuff out there. More stars, more galaxies, maybe even more intelligent creatures than we could ever make contact with. All of these things are in the universe, but are definitely not a part of our own world. Those regions outside our observable bubble of the universe still look and act the same as inside it. It's all the same physics at play, just with various other combinations. But that's not where the story has to end. To get our bearings in understanding how a multiverse could be generated, let's begin with the theory of cosmic inflation, which explains the origin and structure of our universe. Then, because cosmic inflation does not end everywhere at the same time, this leads to the theory of eternal chaotic inflation, which generates multiple pocket universes continuously and without end. It is easy to forget that each of these new pocket universes is vastly larger than our observable universe. But these new universes are not super strange, since they all exist within the same space-time framework that we know in our universe, though they erupt far beyond what we can see in our observable universe. What's more, once these new pocket universes are born, they are totally and forever disconnected from every other universe, including ours. But how to commence cosmic inflation? Some physical material, however minuscule, is required. So from where does this primordial matter come? According to scientists, the answer could be quantum tunneling. Quantum tunneling can create a universe from nothing because in quantum mechanics, things that are classically forbidden by energy barriers can happen by tunneling through energy barriers. So, a universe of zero size, that is, no universe at all, can originate spontaneously by tunneling through an energy barrier and then expanding by inflation. A similar conundrum is that cosmic inflation seems to create energy out of nothing, which would violate the law of conservation of energy, a physical no-no. In fact, the net energy of the universe is zero, because the positive energy of all the matter that is created is balanced by the negative energy of the gravitation. Guth calls it the ultimate free lunch. But what's the evidence for these theories of cosmic inflation, eternal chaotic inflation, and multiple universes? It's challenging, to say the least, considering that cosmic inflation began and ended within the tiniest fraction of the first second of our universe's existence. And eternal chaotic inflation, by definition, cannot be seen, as other universes, arguably generated by eternal chaotic inflation, are disconnected permanently from our universe. However, lines of corroborating evidence beyond the elegance of the equations have convinced many cosmologists to such a degree that cosmic inflation and eternal chaotic inflation have become, in essence, the standard model of cosmology. As for cosmic inflation, it seems to solve, at the same time, several separate enigmas in the origin and structure of the universe. Moreover, cosmic inflation makes interesting predictions, especially about the cosmic microwave background radiation, a remnant of the Big Bang, predictions that have been confirmed and reconfirmed by increasingly precise data from satellites. As for eternal chaotic inflation, it seems to be the unavoidable consequences of the mathematics of cosmic inflation. Once cosmic inflation starts, it seems impossible to stop. However, while there have been tantalizing hints of possible corroborating data, none is convincing yet. In short, cosmic inflation revolutionized cosmology, and if ultimately confirmed, a demanding task. It may come to be recognized as one of humanity's most fundamental realizations. One great question of existence is simply, how big is it? The short answer: it means everything that exists, all there is. But what are the physical dimensions of all there is? A place to start is the size of the universe in which we find ourselves. According to one of Guth's models, our pocket universe may be at least 10 to the power of 23 times larger than our observable universe. Because in order to work, inflation requires at least 100 doublings of the size of the universe, 2 to the power of 100, and roughly 10 to the power of 30. This means that the pocket universe we call home would be 100 billion trillion times larger than everything we can see with our largest telescopes. Thus, it could be said that the vast expanse of our visible universe is but an insignificant speck within just our own inflating pocket universe. And this universe itself is only one pocket universe among an innumerable or even an infinite number of other pocket universes. Put simply, multiverse is just too big, bigger than anything we can comprehend. Regardless, multiverse have many levels. If you find all of this too confusing, we have some other ideas. The simplest version of the multiverse concept is the so-called mirror universe, in which a single alternate universe closely parallels ours, but is also its opposite, such as the Mirror Mirror episode of the original Star Trek television series, in which a landing party mistakenly beams up to a different version of the Enterprise, occupied by more brutal versions of their familiar crewmates. Real-world scientists have used such a concept to explain why our universe has matter when mathematics says all of the matter should have been annihilated by its own antimatter twin as soon as it popped into existence. Another perspective on the multiverse is the brain universe, which describes our universe as one membrane in a vast, possibly infinite stack of membrane universes, but with no connection or means to communicate between them. MacDonald said, Multiple universes might also exist within contained bubbles of space-time, a concept explored in the video game BioShock Infinite. By this reckoning, inhabitants of two universes could theoretically interact should their bubbles connect to each other directly, according to MacDonald. Quantum universes appear more commonly in science fiction. This idea suggests that every decision a person makes spawns a new timeline, creating a new and self-contained universe that follows a different path. Science fiction writers crafting time travel stories frequently invoke the rules of quantum universes to explain how characters can travel to the past and not erase their own existence. Their every choice births new universes entirely, leaving the universe that was their origin intact. But perhaps the most disturbing premise of all is whether the universe we perceive as real is, in fact, a simulation of some kind, as in the movie The Matrix. The simulation hypothesis proposes that all of reality, including the Earth and the universe, is in fact an artificial simulation created by an advanced civilization. While this may sound like science fiction, the notion that human existence might be a simulation has gained traction among some philosophers, futurists, and technologists in recent years. The concept was first explored in depth by philosopher Nick Bostrom in a 2003 academic paper titled, "Are You Living in a Computer Simulation?" Bostrom made a probabilistic argument that if advanced civilizations are capable of creating complex simulations inhabited by simulated conscious entities, then there is a significant chance that we exist within one such simulation. The seeds of the simulation hypothesis originated earlier, with sci-fi stories like The Matrix depicting characters existing inside a simulated reality generated by AI. But Bostrom framed the concept in a rigorous philosophical manner that sparked serious debate on the likelihood that human reality is simulated. Though inconclusive, his statistical reasoning made a compelling case that we should not dismiss the possibility we exist within an ancestor simulation created by post-human civilization. While the simulation hypothesis cannot be definitively proven or disproven with current knowledge and technology, it raises profound questions about the nature of existence, reality, and our place in the cosmos. The notion that our world might be artificially simulated forces us to reconsider assumptions about the limits of science, technology, and our understanding of the universe. The simulation hypothesis has gained traction in recent years based on mathematical arguments stemming from quantum physics and information theory. The basic premise is that if it is possible for sufficiently advanced civilizations to create complex simulated worlds, then it is more likely we are living in one of the many simulations rather than the original base reality. Bostrom argued in his paper that at least one of the following propositions is likely true. 1. Human civilization goes extinct before reaching the post-human stage capable of running complex simulations. 2. Post-human civilizations have little interest in running simulations. 3. We are almost certainly living in a simulation. The implication is that if advanced civilizations have both the ability and desire to run complex ancestor simulations, then simulated worlds could vastly outnumber the original reality. From a physics standpoint, some theorists point to limits on our ability to probe reality at microscopic scales as possible evidence that we are in a simulation. The quantized nature of fields and particles, discreteness of spacetime, and the uncertainty principle may emerge naturally from a simulated reality. However, they seem to be counterintuitive features of a fundamental description of nature. While inconclusive, some argue this points in the simulation direction. In support of the theory, others focus on the exponential trend in computing power and technology's ability to mimic reality in virtual worlds. If this trend continues, then in the distant future, simulated worlds should far surpass the base level of physical reality. This leads to a statistical likelihood that we are living in one of the many virtual worlds rather than a base reality. While a fascinating concept, the simulation hypothesis remains highly speculative and difficult to test scientifically. The theoretical support, however, prompts intriguing philosophical debates about the ultimate nature of reality. Several influential tech billionaires have expressed interest in or support for the simulation hypothesis. Elon Musk, CEO of Tesla and SpaceX, is one of the most vocal advocates. In 2016, he estimated the odds that we are not living in a computer simulation at 1 in billions. Musk believes advanced civilizations would use simulations to explore their history. Peter Thiel, PayPal co-founder and early Facebook investor, has shown interest in the hypothesis as well. At a 2016 conference, Thiel said, "The simulation hypothesis explains the high number of unlikely events that have shaped history." Other tech leaders open to the idea include Sam Altman, CEO of OpenAI, astrophysicist Neil deGrasse Tyson, and Paul Gilding. Their interest often stems from the immense technological advances made in virtual reality and artificial intelligence. With the exponential growth of computing power, creating convincing simulations seems increasingly possible. Still, many of these leaders admit the hypothesis cannot be proven either way with current knowledge and technology. Much more progress in fields like quantum computing would be needed to test it thoroughly. Their openness highlights that even top industry experts cannot completely rule out the possibility we live in an advanced simulation. Some scientific observations have been interpreted as evidence that we could be living in an artificial reality. Here are some key examples. Key theory of quantum mechanics describes subatomic particles behaving in strange, unpredictable ways. Some argue this could be because our reality is simulated and small glitches occur at the smallest scales. Besides, astrophysicists have calculated fundamental physical constants, like the speed of light or the mass of protons, that seem finely tuned to allow for life in our universe. This fine-tuning resembles how parameters are set in simulations. In addition, there seem to be limits to how finely we can measure and divide space and time. This could be because we live in a pixelated matrix with a finite resolution, much like a video game. And as mentioned previously, philosopher Nick Bostrom made a statistical argument that at least one of these must be true. 1. Humanity goes extinct before reaching a post-human stage. 2. Post-human civilizations lose interest in creating simulations. Or 3. We are almost certainly living in a simulation. Some report experiencing glitches or déjà vu in reality, interpreting these as artifacts of a simulation. However, these experiences are subjective and prone to cognitive biases. While intriguing, each observation has alternative explanations, not requiring a simulated reality. More research is needed to conclusively demonstrate we live in a simulation. Absent direct evidence, the simulation hypothesis remains philosophically interesting but scientifically unproven. While intriguing, the simulation hypothesis has some major flaws worth considering. Several logical and scientific arguments challenge the likelihood we are living in an ancestor simulation. First, creating such a complex simulation would require astronomical computing power and energy far beyond what humans can currently achieve. The processing capability needed to generate a simulation indistinguishable from base reality appears infeasible now or in the foreseeable future. While computing does continue to advance rapidly, the scale of advancement needed to simulate complex consciousness and reality itself remains distant. Additionally, there is the question of motivation. Why would an advanced civilization want to create such a simulation? And how likely is it that a civilization advanced enough to do so would choose to? The hypothetical rationale behind creating an ancestor simulation, such as for research or entertainment purposes, fails to provide a convincing case such a simulation would actually be commissioned. The simulation hypothesis also raises difficult philosophical questions about consciousness and reality. If base reality is just a simulation, what created that higher level of reality, and so on? The The proposition that consciousness and reality could be simulated suggests existence itself has an uncertain ontological foundation. This philosophical dilemma of infinite regression makes the simulation hypothesis difficult to ground convincingly. Current knowledge of physics, computation, consciousness, and reality offers several challenges to the likelihood we are living in an ancestor simulation, while future discoveries may shed new light. At present, the simulation hypothesis remains philosophically intriguing but scientifically uncertain.